goal of developing and promoting a robust, usable and scalable means of delivering solutions to complex problems that a sustainable and globalised society needs to thrive in the 21st century. Practically, what that means is that we're 800 members worldwide currently in over 48 countries. And what the DS does is to give access to research papers and theses, awareness of events, calls and jobs, reduced publication fees, reduced event registration fees, and the ability to develop your career. We proactively support and promote designers of tomorrow and researchers of tomorrow through PhD summer schools, young members events, interaction with your peers and resources, particularly for younger members. If you have a particular interest within design, you might align with one of our special interest groups who are running workshops and different design activities and research activities throughout the year, particularly at our conferences. If you want to know more information about what the DS is and what it does, you can go to the website designsociety.org. And I'll pass over to Claudia to introduce Dan to you all.
Ross, thank you very much for the introduction. Welcome to Dan for the talk today. We are starting the Design in Society seminar series again. Dan is going to talk about complexity today. I suggest that you get started afterwards. If you've got any questions, collect your questions in the chat already. We can ask questions afterwards as well. And if we have a lot of questions, then I'll try to bundle the questions and sort of ask the questions that are more of sort of general interest to the public rather than very specific and technical question, because I'm sure you can ask those to Dan and specifically and personally afterwards. So I think over to you. I suggest we probably turn the microphones and cameras off while you talk, and then we can bring them on again afterwards.
Well, hello everyone. Great seeing you all. Thank you, Claudia. Thank you, Ross. I'm so happy to see more than 10 people in the audience. I just gave a seminar the other week. There was only a single person online. I was so happy. I thanked the guy. I told him, thank you for coming to hear my talk. He told me, Professor Braha, you don't have to thank me. I'm the next speaker. So with that, I'm very happy to see more than 10 people in the audience. So let me share my screen with you. Do you see it, everyone? Yeah?
Yes, we can see your screen.
All right. Yeah. So, many people in the community hold the belief that there is a difference, there is a distinction between design and science. Science is concerned with extracting knowledge based on natural phenomena, and design is concerned with, utilizing that knowledge to create new products and change the environment. As a matter of fact, I would like to convince you that the distinction between science and design is very vague, is actually quite artificial. Both science and design are concerned with emergent phenomena that are the result of complicated interactions between diverse systems. And that's the common thread between those systems. Before I will, focus on the topic of today's talk, which is presenting complex design network theory, I would like to give a brief. Sorry, my screen is. I would like to sort of provide a sort of an overview, explaining, how the idea came to birth, and also demonstrating that the concept of interactions and relationships between different design elements is the underlying concept, is the thread connecting all of the work that I did in the past. And in a way, the work that I did in the past anticipated my involvement with networks today. So it's very interesting to take a look at the overall picture. So, between 1991 and 1998, I was involved in developing a theory called formal design theory. The outcome of that work is summarized in a book, which is called The Mathematical Theory of Design, published in 1998. And the concept of relationship was fundamental to that work. For example, one aspect of the theory was to develop a model of artifact representations, which is based on modules and relationships. In a way, this is the first instance of representing artifacts using hypergraphs, which is a more advanced concept than graphs. So that's actually the first use of hypergraphs as a way to represent artifacts. But not only artifacts, but actually the function space was also represented using the concept of modules and relationships. Another aspect that involved the concept of relationship was the use of closure topological spaces and category theory to represent the mapping between the design, the artifact representation and the function space. So I was working on a model where essentially what you do, you start with some specifications or functions or concepts, or call it whatever, and what you do, you refine it by applying a variety of operators representing using closure topological operators, and eventually you come up with some refined space of requirements, which you map to the artifact space, and then you apply a variety of refinements, expanding the product, coming up with eventually coming up with the final result, and then you apply an analysis mapping connecting the artifact space to the function space. So that was an ideal cycle. Another aspect, this kind of model was very naive because it didn't take into account the evolutionary aspect of design, and that was done by expanding the model and taking into account the evolutionary, or by developing an evolutionary model for the design process. This was in a way a coupled design process. So essentially, what you do, you expand both the artifact representation as well as the function simultaneously, and the methodology to capture this coupled design process was using automata theory and logic. As a way, I was influenced by design paradigms, the AI in design, and my goal was to create a universal machine, sort of, that can represent any design process whatsoever. So regardless of the type of methodology or model that you apply, the question that I try to basically address is, can you build a universal design machine? And that was the universal design automata model that is basically a coupled design process. There are many results came out of this work, including soundness result, and more importantly, results related to the computational complexity of design, demonstrating for the first time, I think, in the literature, that design is really hard. It's a tough process, right, in a formal way. We know that it's a very difficult process, but that was a sort of a way to capture it by a theorem that shows that design is a very tough process. Later on, I combined the closure topological spaces with the coupled design process representation, and introduced an extended model that is a closure topological space along with a coupled design process. That was the work published with Yoram Reich in 2003. And people call it in the literature coupled design process, but actually the coupled design process was done already using the automata theory. At that time I was thinking that I'm the only crazy person that applied topology actually in design. That was quite foreign to many people. I was happy to learn that there was another theory by Yoshikawa in Japan, then the president of the University of Tokyo, developing a theory based on point set topology. And so I was very happy to discover that. As a matter of fact, this paper in 2003 demonstrated that Yoshikawa's theory is a special case of the coupled design process model. I was invited by Yoshikawa and Tomiyama and other people to a variety of conferences in Japan and Cambridge University in the UK. Here you see when I was young and beautiful, and also you see something very interesting, that the color of your hair is always becomes the same as the color of the hair of your peers. So that's another rule of life. So here you have another, you know, those what kind of historical picture with Susan Finger, Tomiyama, and myself. That was a very interesting time. You know, I was very happy that down the road, this model became the foundation and impacted quite directly the literature on design thinking and design theory in general, in particularly what people call CK theory, which is in a way an extension of the coupled design process. So that's a lesson for young people, that if you have a crazy model, go with that. Eventually it will create an impact. Going down to the additional development, another development that incorporated the concept of relationship was developing an information theory of design, essentially defining the entropy of the design process and the design product. So that was I think the first attempt to incorporate information theory in design. A related concept was I was starting on developing a variety of techniques to measure the structural and functional complexity of design. It was also it had strong relationship to the information theory of design that I developed. The work on measuring design and functional complexity, the work on information theory, and the work on the computational complexity aspect of design impacted quite significantly the literature, the entire growing literature on measuring design complexity. You know, since then people started to apply very similar techniques. So that was gratifying. With respect to complex design network theory, let me explain how the idea came about on that side. So I was working with colleagues on working in the area of the design structural metrics approach methodology. This work led to a generalized design structural metrics model that really captured, that provided really a general model relative to what existed up to that point. At the same time, I was developing also the concept of complex concurrent engineering. I think that was the first time that the concept, that the word complex concurrent engineering was applied. And here I introduced a variety of principles influenced by complexity theory, including the iteration principle, concurrency principle, the composition principle, and the stability principle. A variety of principles that led down the road to my interest in complex design network theory. The work on the generalized design structure metrics, influenced the literature on design iterations quite significantly, and also led to my personal interest in the area of design network theory. In a way, this work was also influenced by my work in the area of temporal network theory. So that was really a paper that we wrote where we first analyzed network as time series entities that change over time. So that was the first paper in the area of temporal complex network theory, and it created an impact on me personally, leading to my own interest in the area of complex network theory. Of course, I was influenced by complex network theory in general, a theory that was introduced by physicists, and that all of those influences led to my interest in the area of complex design network theory. This theory influenced quite significantly the emerging literature on complex design networks and engineering systems in general. So you see how ideas are connected. And what I'd like to do now is to sort of further explain the principles of complex design network theory. and eventually presenting some results that are quite shocking, and I would like your opinion about that, and hopefully we're going to have some nice discussion. So, complex design network theory deals with the idea of representing design using networks. So here you see a network with 889 nodes and 8,178 links, describing a process leading to the design of a certain hospital. And so when I say a network, what you have are typically you have engineering nodes that could be people, tasks, components, subroutines, logic gates, whatever you have in mind, connected by information flows, which could be engineering change orders, parameters, specifications, signals, and so forth. So over the years, I've developed a variety of laws of complex design networks, and I would like to describe some of them. So the first one is sparseness. So what do I mean by sparseness? The basic idea is that networks have only a small fraction of the possible number of links. Now, it sounds trivial, but it has actually quite strong implications for the dynamics of systems. So, just to illustrate my point, so if you take, for example, the design of a hospital, the number of nodes is 889. The number of links, it's 8,178. If you calculate the density of the links in this network, so it is less than 10%. Actually, very, very small number. And typically, this number is very, very small. So this is quite surprising. You expect that the number of links would be larger, right? Because the larger the number of links, the better the performance. But this is not necessarily the case. Another observation is the small world observation. Well, the idea is that networks are clustered, but have a small characteristic path length. So what I mean by that is that networks have high level of modularity. They're highly modular, which is a good property in design. But at the same time, it's the distance between any two nodes is very short. Now, those two aspects, those two characteristics, always go against each other. I mean, for example, if you have a crystal, a crystal is highly modular, but the distance between any two nodes is very large, right? Well, design is not a crystal, right? I mean, any design activity is not a crystal. On the other end, it might be random, right? Completely random, where nodes completely connect to each other in a completely random fashion. Well, if you have a random network, you have very low level of modularity. However, the distance between any two nodes is the shortest possible. So here you have this trade-off between modularity and distance. And as a matter of fact, real-world networks is always a mix between them, right? So real-world networks achieve a balance between modularity and the effectiveness of sending information between any two nodes in the system. So that's one property. Just to illustrate my point, so if you take a variety of networks, for example, take the vehicle design. So the average distance between any two nodes is 2.88, right? 88, right? If you have a random network of the same size, the average distance between any two nodes is very similar, right? So you see that the real network achieves the same effectiveness as a random network. On the other hand, the clustering coefficient, it's a measure of some measure of modularity, is much larger, right? 0.21, much larger than the level of modularity of a random network. So that's the idea, that you achieve modularity, but at the same time, it's very easy to send information between any two nodes. Another set of rules are related to the degree distribution in the network. So what do I mean by that? So a degree is simply the number of links, the number of information flows associated with each node in the network. So it turns out that the degree distributions of nodes in the system are heavy-tailed. And what I mean by heavy-tailed, I mean that the distribution are right-skewed or fat-tailed distribution. The meaning is is that you have very few nodes that have a lot of, have huge degree relative to all of the others that have small degrees. So most of the nodes have small degrees, while you have those small numbers of nodes that have that dominate the network, that have a large number of degrees. We call them design hubs, and those hubs. So since the networks typically are directed, then you have the in degree, meaning the number of information flows coming to a node, and you have the number of information flows going out of a node. So in a way, you have the result tells you that you have nodes that are high receivers, meaning they receive a lot of information. You have few nodes that are high generators of information, right? And you have also brokers. Well, we don't have time to expand this aspect, but the point is that you have those few nodes that receive a lot of information and generate a lot of information, and they determine the dynamics of your system, right? So those are the bottlenecks of any design system, right? So that's one observation that we get here. We have also that this asymmetry between in and out. So typically, sending information is more right skewed than receiving information. Again, all of those goes to or has relevance to the dynamical aspect of any design. Another aspect of another rule, if you want, of design is the idea that the structure itself provides information about the dynamical process taken on top of any design network. So that's something important. The idea is that the design network itself provides direct information about its dynamics and about its behavior. So if you show me a network, I can simply take a look at the network, and I can tell you how any dynamics will behave on top of that network. Yeah, I have a story about. Well, I don't have time for that, but just to tell you about a certain aerospace company sending me information about the network. So I was trying to analyze the network, and I see that everything that I know about networks do not apply. So I send an email back to this aerospace company, and they're telling me that they didn't send me actually the right data. They extracted a lot of information due to proprietary reasons. And so immediately, just by taking a look at the network, you know that someone is cheating, right? Because that's not the real network. So that's about what I mean by structure-based dynamics. Now, how do you represent it, right? How do you represent it? Well, it turns out that that the design dynamics is controlled by the extent of coupling and correlation happening in the network, right? And there is a way to quantify this aspect of coupling. Coupling is a function of the network itself. Coupling can be represented as a function of the structure itself, right? And when I say dynamics, you can talk about any dynamics. For example, you can represent, for example, the dynamics of defect or error propagation on top of network. So that's something that you see on the right, in this simulation. So it can represent, for example, failures on top of power grids, failures of communication systems, failures of mechanical systems, of computer networks. Any type of failure can be represented as a dynamical process happening on top of real networks, right? And you can also represent the process of design itself as a network. So you have people that interact with each other, and the blue circle represents open problems, red circles represents closed problems. And I would like to say the blue nodes represents closed problem, the red represents open problems, and then you have this sort of iteration going on in the system. Eventually the network will converge or maybe not. And again, it all depends on the level of correlation and coupling within the system, which is a function of the network itself, right? So eventually what you get is that on any design network, you have a phase transition phenomena, very similar to ferromagnetism in statistical physics, what you have here is that as you increase the coupling in the system, suddenly you will experience some phase transition in the behavior of the system. You will experience some qualitative change in the behavior of the system. So if you represent product development, it means that the total project time or budget will suddenly increase dramatically as you increase the coupling of the system, which is a function of the network itself. And it could be that as you increase the coupling of in the system, suddenly the number of defects and errors starts to rise quite dramatically. And again, everything is a function of the network itself, right? That's the surprising part. So for example, you might say, well, networks are random. Well, if networks are random, then you have the phase transition can be depicted using those diagrams. So you see the blue diagram represents sort of the area where the design becomes stable. And what you measure is basically is that on the y-axis, you have this coupling coefficient that, again, is a function of the network itself. And on the y-axis, you have another coefficient. This is the autonomy parameters that really represents the autonomous behavior of any node in the network, regardless of its neighbor. So in a way, any design process is a trade-off between this autonomy at the level of individual nodes and the coupling and the dependency between various nodes in the system. And the phase transition depends on the relationship between them. So if the network is completely random, then it can be shown that as you increase the average degree in the network, meaning the average degree is really representing the average number of links associated with each node. So as you increase the average degree in the network, the system will become less and less stable, right? Less and less stable. So that's the result with respect to random networks. But we know that real networks are not random. So what do you have in real networks? In real networks, you have correlations. So what you see here is that the phase transition is really a function not just of the average degree in the network, right? This is simple. It is also a function of the correlations and coupling within the system, right? And again, all of the correlations are really a function of the network itself. So the idea here is that positive correlations between any two nodes in the system will lead the system towards instability, right? Will lead the system towards instability. As a matter of fact, if you want to improve the system, you need to have negative correlation between any two design elements within the system. So here you have the correlation here will shift the line separating the phase transition upward, meaning will shrink the area of stability relative to the area of instability, right? So by the way, when you measure the correlation in real systems, so here you have vehicle design, you have real estate design, you have business strategy design, you have microprocessor design, biofacility design, car design, equipment design. In all of them, the correlation is very small. And again, I don't have time to explain how they measure, how they do it actually. But the basic idea is that the theory predicts low correlation. That's indeed what you get. And sometimes you get even negative correlation. Right? So by the way, when you see a star here, it means that it is significantly different from zero. So you see in all of the cases, it's actually pretty much zero, except for this system, which is the real estate system, which seems to me violating what I expect. And I wonder if there are problems with that project. So the next set of laws are related to the robustness and fragility properties of real design systems. So what do I mean by that? So the idea here is that the dynamics of any design system is ultra error tolerant, right? So now I'll explain what I mean by that. However, it is highly vulnerable to all kinds of perturbations targeted at design hubs, right? So in general, if there is some problem with any node in the system, any random node in the system, the system will be quite stable. However, if you try to perturb and you try to sort of change the properties of the design hubs, then you might lead the system towards collapse. Another property, related property, is the idea that any design system is sensitive to changes related to those design hubs, which means you have a leverage and you can actually change the system to achieve some results that you want to achieve. So the idea is that preferential design policies that focus engineering efforts on those design hubs will lead towards improvement. So just briefly explain those, the idea of robustness and fragility. On the left-hand side, you see the idea of robustness, right? So the x-axis represents the percentage of nodes that you perturb, that you sort of modify. And the y-axis represents the average time that it takes for the system to converge to a design solution, or the total number of defects in the system, or error in the system, or whatever you measure. So if you perturb the nodes in the system randomly, right? So you take 2% of the nodes in the system, and you perturb them randomly, or you take 4% and you change them randomly, and so on. You see that the average convergence time will go up, right? Which is bad, but it goes up quite slowly. However, if you perturb the design hubs in the system and you sort of distort their behavior, their local behavior, and you make them more coupled to the neighbors, you see what happened to the behavior of the system. Suddenly, it takes more time for the system to converge. Suddenly, you have more problems propagating on top of the system and so forth. That's what I mean by robustness versus fragility, right? On the other end, what is sensitivity and leverage? Well, you have a system, you can actually improve the design hubs, right? You can improve the design hubs, you can protect them, you can reduce the coupling relative to the neighbors. So, however, if you do it randomly, if you try to reduce the coupling of nodes randomly relative to the neighbors, then you see that there is an improvement. There is an improvement in the convergence time, right? It will go down, but it goes down very slowly. However, if you improve the design hubs in the system, right, you see that there is a significant improvement in the system. So as a general rule, you see actually that you achieve twice as faster process by focusing on those bottleneck nodes in the system, in any system, right? Any design, any network that you have, any design network. So that's the idea of robustness and sensitivity. And now we come to the focus of what I wanted to show you today. And I hope you are buckled up, because those are quite startling results, and I don't have an explanation for it. So you'll have to help me. So this is the idea of building blocks in any design networks. So the idea is that any design networks have some key design circuit elements that evolved over time to perform particular tasks. So the idea is that, imagine that you have, so what I want to do is I want to introduce a concept which I call design spectroscopy, right? So the idea is that you have a variety of systems that you want to analyze, and you put it into this spectrometer, and it gives you the spectrum of each of those design systems. And I want to show you that any design network has the same spectrum. It leads to the same spectrum, and that's a puzzle. So that's what I want to show you, that if you analyze different systems and it leads to the same spectrum, right? So what do I mean by spectrum? I need to expand the word spectrum. So here you have a variety of systems. You have vehicle design. You see the size of the nodes represents the hubs. You see the hubs, right? Represents the degree. Colors represents the communities that exist in the system. So this is vehicle design. You have real estate design. You have business strategy design, microprocessor design, bioscience facility design, vehicle design. Okay, right? But vehicle design is different. This is a company different from the first company, right? So completely different system, and mechanical equipment design, right? So when I say design circuits, what I mean is that I'm going to analyze the prevalence or the frequency of different subgraphs within the network. So for example, here you have all of the 13 possible subgraphs that includes 3 nodes, right? So this is a directed network, and those are all of the 13 possible subgraphs that can exist in any network. And then you have also 4-node subgraphs, and you have 199 of them. So here you have, all of the 199 subgraphs, right, that can exist in the network. All of those represent different configurations of the way that nodes interact. So, for example, think about this real-world network, just to illustrate my point. So, Claudia, you are the boss. We know that. So you work with Mario and me here, and you see the interaction between us create this type of subgraph. You see, you send to me information, you send to Mario information, and Mario send to me information, right? So, and here you have another instance of this node, which is called the feed-forward subgraph, and you have another instance. However, this subgraph, this interaction here between 4, 5, and 6 is actually different, right? Because this is an interaction where any 2 nodes interact with each other. So this subgraph is called a click, right? Or click. So the goal here is to count how many subgraphs do I have in a network of each type. And I want to see whether I get any pattern that is interesting, right? So, the general concept that you start with a real network and then you randomize it somehow. So here you randomize the network, right? You get a different network and you see what happened. In this case, there is only one instance of the feed-forward node, subgraph. So in the real network, there used to be 3, and now there are only 1. So by sort of comparing the real network relative to a random ensemble, you can check whether the prevalence of a particular subgraph is unique or not, right? That's the general philosophy. Well, so moreover, what you want to do, you want to explain the functionality of those different subgraphs, right? So in order to do that, you need a model. And so the basic model that you can consider is a system where people interact with each other, they solve problems. So you have open and closed problem represented by the red dots and the blue dots. And right, so there is some dynamics going on that might look something like that. You see open problems arise, closed problems arise, and eventually you come to some sort of convergence. Well, the idea is that now you can analyze the behavior of this model relative to the subgraphs, right? So you want to I raise a hypothesis that design networks are really concerned with the synchronization and the concurrency and the sort of the collaborative aspect that lead to a final solution. So here you see two types of behavior that can happen in the system. The system can converge over time to a solution, or the system might diverge, right? You might have two possible solutions. So the system might synchronize or might diverge. Now, you take all of those small subgraphs and you create a measure of synchronization. So this is like the probability that if you run the model on a subgraph, what is the probability that it will converge to a solution? What is the probability that it will synchronize to a design solution? So here you have a map that shows you this synchronization probability, right? So you see the blue meaning that there is full synchronization, and as it becomes red, it means that there is less synchronization. So you see what happens. The feed-forward loop converges or synchronizes much faster on average relative to the mutual in, relative to the mutual cascade, relative to the click, and so on. You see the blue area shrinks, meaning the extent of synchronization is reduced depending on the subgraph that you're testing. All right. So going back to the story of networks, so here you have the subgraphs ranked by their synchronizability probability, right? So it's like, imagine that you take this picture and you boil it down to some measure which we call the synchronizability measure, or SM measure. So you see the subgraphs ranked according to their SM measures. And so you have, subgraphs that have high synchronizability, moderate level synchronizability, and so forth. And here you have the ranking of the subgraphs in the real networks, regardless of the model. Just count how many do you see in the real networks, right? So what you see here, quite interestingly, that first of all of the networks maintain the same ranking pretty much. So if a subgraph is prevalent in one network, it is also prevalent in the other at the same level, but also it is actually associated, quite correlated with the SM measure, with the measure of synchronizability, right? So you see it has the same order here. Of course, you can test it more statistically from a statistical perspective. So here you have sort of Spearman rank correlations showing the correlation between the prevalence of the subgraph in the different networks. So you see that indeed there is high correlation between the prevalence of those subgraphs in different networks, right? Also, if you extend it to 4-node subgraphs, you see that there is high level of correlation, meaning all of those systems that are completely different from each other actually are highly correlated in terms of the prevalence of those subgraphs that I mentioned at the level of 4 nodes or 3 nodes. And so you later, of course, you can conduct more serious analysis. You can also check the correlation between the SM measure, the synchronizability measure, and the prevalence of the subgraph in the real networks. So indeed, you find high level of correlation, meaning you find that subgraphs that are highly synchronizable, right, that are easy to synchronize in according to a model, are also prevalent in the real networks. So there is it means that those subgraphs, that design networks are built based on those key circuits that are supposed to lead to high level of synchronization in any design networks. You can also test the sort of the correlation between the SM measure and the prevalence also at the level of 4 nodes. And in all of the cases, you pass the test at a very high level of statistical tests. So synchronizability is a basic feature of design networks, right? All right. So now I don't have much time. I think I have about 5 minutes or so. So I'll try to wrap it up here. So the next question is that you want to test whether a subgraph, the prevalence of a subgraph in the network is really unique. And the way to do it is to compare the prevalence relative to a randomized ensemble, as I mentioned, right? And once you do that, you can create what you can call the subgraph profile of the network. So here you see the different networks and the subgraph profile, which is basically the z-score, right? Going back to statistics, the z-score, which is the real frequency minus the average frequency in the randomized ensemble divided to a standard deviation. So you find that the profile of those subgraphs in the different network is pretty much very similar. That's what I call by the spectrum. The spectrum is very similar to each other, right? There are some deviation, but when you look at it, you say, wow, that looks very similar. And moreover, it turns out that the association between the synchronizability property of subgraph is associated with the z-score, meaning the higher the synchronizability, the higher the z-score, meaning the higher the synchronizability property of a subgraph, the more prevalent the subgraph appears in the real network relative to a randomized ensemble. That's the idea here. So I'm going to skip because my time is past, and it gives you the same idea. But here you find results that are most startling, meaning instead of measuring the z-score, you measure another score which is called the RD score, which is basically the real frequency in the real network minus the frequency in the randomized ensemble divided by the sum. So this is slightly different from the z-score, right? So instead of asking what is the significance of a subgraph, you want to ask whether the frequency of a subgraph is really different from the frequency in the randomized ensemble. So for that, this is the purpose of the RD measure, the relative difference measure. So when you do it at the level of the RD measure, then you find that the spectrum is amazingly the same across different networks, right? Again, all of those are different systems, the same profile in all of them. Same profile, and again, you can show that if a subgraph is highly synchronizable, it also has a high level of RD score, right? That's the idea, right? So showing again the relationship, the association between the synchronization property and the prevalence of the subgraph in the network. And again, the profile here looked the same to me. I don't know about how do you think about it, but that's something quite amazing. Well, my time is running, so let me just summarize and say that large-scale design networks share repeated patterns of interdependent activities. You might call it design routines that are universal across many distinct organizations, completely different organizations. You want to say that the abundance of these design routines is highly correlated with their ability to synchronize and coordinate the design activity. So this seems to me a very sort of basic property of design networks in general. And you might explain it in terms of evolution and adaptation and self-organization. So you might say that any design network has a nested hierarchical structure where you have a subgraph within subgraphs type of organization. And so there is an advantage for highly synchronizable subgraph because once you converge at the lower level, it leads to convergence at higher level, and eventually it leads to high level of coordination at the level of the entire network as a whole, right? And it goes, you know, I don't have time, but you might explain it also in terms of temporal networks in some way. And you might also explain this, the last slide here, that you might want to explain it in terms of biology in a way. You might want to say that, you know, the design that we actually observe is the result of an evolutionary process, right? We didn't start with the design that we see. It went through many iterations over many generations, right? So, you know, you start with some variation of subgraphs in the network, right? So you have diverse abundance of subgraphs in design networks. Some provide an advantage, right? Like synchronization and coordination. And over time, there is a process of selection and transmission. You know, there are all kinds of processes like mimicry, copying, learning, reuse, best practices, and eventually we select. Those selective pressures lead to selecting those synchronizable subgraphs, right? And that leads to new design networks. And this is the reason why we see in real networks subgraphs or key circuits that have certain properties, like the one I tried to convince you related to synchronization and coordination. So with that, I'll open the floor for discussion. Thank you.
Thank you very much for your talk, Dan. That was extremely interesting. I think while everybody is composing their question, maybe I can start us off. Okay. I mean, as you probably know, I've also done quite a lot of product and process modeling. And what I found is that whether there is a lot of connectivity in my model or not depended on what I choose to put into the model. And we were really struggling with this when we were modeling change prediction, because when you sort of include things like cost or weight, then all of a sudden everything is connected to everything. And also in the size of the modules and how much we broke them up influenced a lot on how much connectivity we would then find in the analysis of the network. So my question to you is, how much is what you're finding the result of the modeling choices that you put into generating the network or the network itself?
Right, so it's a great question. So indeed, those networks were created by asking people simple question. Please provide the design activities that most influence your activity. Simple question. So this is not something extracted by the observer, by the design scientist. It is really something that people reported. So the designer themselves, tell you what's important and what's not. So you might say that there might be errors, with respect to one design network, but I don't see any possibility of having an error with respect to reporting with respect to so many networks. You see, that my point is unlikely that the similarity that you see in the profile and the spectrum that you see, which is actually the same or pretty much the same, is the result of an error of reporting, missing. There could be some missing relationship, missing interactions, but it is independently extracted, not by the scientists, but by the people themselves.
I do accept this, but I still find it's always a bit of a problem because people run out of steam with giving you connections to things. So I'm sometimes wondering whether there are 7 connections or 10 connections or something is more that this is the attention span that somebody has in enumerating what activities or connections they have as opposed to the ones that they actually do have.
First of all, I agree with you that we found it also that the fact that the our degree, like the number of information flows going from a node, are different from the patterns observed with respect to in degree. The reason for it is the bounded rationality aspect that you mentioned. Indeed, people will list less tasks that affect them. But when you analyze the out degree, it's completely invariant to what people report. The out degree are completely invariant to what people report. This is the way to correct for error. So you might say, yes, there might be an error with respect to in degree, but with respect to out degree meaning, the way that I affect many others, right? You see my point? Let me give you an example. It's like when I speak to an audience, so the individual person can absorb only a limited information from me, right? Because they have limited span of ability to absorb information. However, I can speak whatever I want and it goes to so many people. So there is no limitation with respect to out degree. There is limitation with respect to in degree. So bounded rationality applies at the level of in degree, not out degree. In that sense, there is less risk of error in the analysis.
This is true, but it still depends on what you define as a connection, because you might speak to many, many people, but whether those many, many people listen is an entirely different question. Of course, everybody here paid 100% attention to what you said.
That's correct. I would say that I would really encourage the young people in the audience to collect data and verify or falsify the result.
Great. I think we've got a question from Martin. Martin, do you want to ask the question yourself?
Okay, I was looking at these graphs and thinking that if what the graphs represent are people talking to each other and who can give orders to whom, that if what matters for what you're optimizing for or evolving towards is synchronizability, then what that leads to you is a completely Stalinist top-down control measure. And the Soviet Union in its worst days got to be extremely synchronized, but not doing a very good job for optimizing anything else. And I was wondering what happened if you have evolution pressures that aren't synchronizability, since what these graphs that you're showing us are not totally Stalinist. People are actually interacting with each other and influencing each other. There's got to be a reason for that.
Yeah. So, yeah, I mean, first of all, that's the point that I wanted to, that I try to explain the result in terms of evolution. The point is that all of those networks are not designed like the Soviet Union, as you mentioned. Those are self-organized. That's the point. The point is that there is no planner, no single planner, designing those networks, actually. Those networks are large networks. There is no, you cannot design them by a process of optimization. Those are self-organized networks. And yet, despite the fact that they are self-organized, what you find is this type of patterns. Let me show you again. You find that the spectrum is the same across all networks. There is no one designed them. No one thought about having the same spectrum. Yeah, you understand? I want you to understand the deep idea here. There is no process of optimization here. Those networks are reported as is. As is, there is no optimization here. If the network is small, if it includes only 5 people, you can design them, you can optimize. But those networks include hundreds of nodes.
But that doesn't say that they are not controlled. And I think Martin's question was about control in the network as opposed to optimization.
In what sense they are controlled? That's my question to you. What sense? I mean, there is some process, there is methodology, right? Definitely, those networks have incorporate methodologies, right? Design methodologies of all sorts, right? So those design methodologies are global constraints on the network. I agree. Those are global constraints on the network. On the other end, you have also this local interaction between different design elements that are modified over time, that evolve over time. So the result of what you see is the combination of these global design methodologies along with the adaptation at the local level. So you have self-organization and design methodologies leading to the same picture.
This is true, but in organizations, they're putting a lot of effort into trying to get, for example, cross-team collaborations going. So they would actively try to direct some of these things, right? Because you often have got close collaboration across disciplinary boundaries or product proximity or something. And then somebody actually comes along and tries to get people to communicate, like systems engineering departments or something.
Absolutely, I totally agree with you. There is no argument that this is the result leading, but the question is, what, even if you apply such rules, what could the hell explain the similarity, the numeric similarity in the profile? Those are actually the same numeric profile. It's like you have 2 products, right? You have to think about the application of spectroscopy in physics, right? You have 2 materials, and they generate the same radiation. They're actually the same product, the same entities. I find it puzzling to find that you find the same profile, even though we apply the same methodologies, the same and so forth. Nobody designed this profile ahead of time. This profile is not optimized. It cannot be optimized because no designer is thinking at the level of subgraphs. Those subgraphs, nobody designs those subgraphs. You have many combinations, and you have, the graphs includes, if you test 5-node subgraphs, you have, millions and millions of combinations of interactions. You cannot design them ahead of time. There is no single planner.
Do we have any other questions or views on this from anybody in the audience? Paul?
Thank you very much for the presentation. I'm along a similar line. Of course, in systems engineering, the big topic of the last 5 or 6 years has been digital or model-centric engineering, where the idea is to more strongly interconnect members of a design team using information systems. How would you approach the question of when, where, and whether it's a good idea to do that using some of the results of your research?
So I think the idea here is first to identify those configurations that have utility, right? That contribute toward collaboration, synchronization, and maybe other features, by the way. Maybe there are other features that any design activity contributes to. It could be innovation. It could be, fidelity. It could be quality. It could be all of them. One is to develop actually separate model for each one of them and see whether the model predict high correlation between all of those features and the actual prevalence in the real network. So once you discover those configurations that are useful, you can actually start to build the design process from the bottom up in a way. So if you find that you lack certain type of useful configurations in the system, you can actually you can you can begin rewire collaboration in order to contribute to the overall goal of the entire system, right? So it's a sort of, my recommendation is to first identify those configurations that are useful, then start to observe the system, the network, rewire some of the links in order to increase the prevalence of those useful configurations, and at the end, it will lead to a system-wide, behavior, the behavior that you want to achieve.
Martin, do you want to reply to this since you replied in the comments?
I was thinking about what a development process actually looks like, and I was thinking that nobody has the graph structure in their heads when they're doing any kind of project management. Exactly. However, you do have managers making decisions about how to slice projects up into tasks, who to put into teams, etc., such that bits of interaction are, rather than other bits of interaction, are being caused or at any rate pushed.
I totally agree. That's the idea that I try to convey here. That you have all of those mechanisms, local mechanisms in design that contributes in a self-organized fashion to what you see, to a system which is self-organized. So indeed, it is the result of all of those mechanisms that you mentioned. I totally agree. The idea, we need to understand those mechanisms. We need to, and those mechanisms lead to the interaction that you observe. But there is no single planner that says, oh, I would like to achieve this profile, so let's apply this methodology and this type of collaboration and so forth, and eventually, in order to achieve a certain profile. That's not what you do. It's all a bottom-up approach, where you apply at the local level some mechanisms that self-organize over time to create a pattern of interaction, right? That lead to the pattern of interaction that you actually observe. So we actually agree, and it would be nice to think about this self-organization. And in a way, my point is that design is not different from biology, and that's something I would like to mention. We think that design is different. It's not. It's not. We think. We have this illusion that we design something and we are free of self-organization. We are free of those mechanisms. And I would like to say that there is much similarity between biological system and design system. And we have to think about design like biologists. And we might get progress also if we do that. I don't know if you agree with me. I know it's a bit something not conventional.
I think this, again, the question is too much. What are the choices that we are making in all of this? And I think as humans, we make choices and biological entities don't to the same extent. However, we should probably not digress into free will and all of those questions. Do we have any questions maybe more focused on Dan's talk? I think we got a thank you from your
before, let me just, if I may, just I want to share with you if someone is interested to read more. So just I'll put it on the screen so everybody can see it later. So, you know, those are some papers related to formal design theory, you know, the use of topology, category theory, you know, measurement of design, structural complexity, as well as some references related to complex engineered systems.
Why don't you put this into the comments, then people could pick this up.
Okay. So I just put it here if someone wants to see it in the video or something.
Yeah, but it's easier if you just put it in the comment and then people can pop it up in the comments.
Okay. All right. Well, never mind. It's too cumbersome to do it now, but any other questions?
I think since our allotted time is over and we all probably have to move on to our next meetings, as it is in most people's professional life, we should probably thank you very much for your talk. It was really, really interesting, and it was nice to see you at a Design Society event. And do come in person when they have in person again.
My first meeting in a Design Society, you know, I typically minimize my travels. I'll try. You're doing a great job. Thank you, and I'll be happy to visit you in the future.
Thank you very much. Goodbye, everybody. Thank you very much for attending. We'll start the series, the Design Society seminars, up properly next year. So watch this space. Bye.